Hi, everybody, and welcome to this presentation on Couchbase ACID transactions, part of the Connect Online developer track. My name is Graham Popel. I'm a principal engineer on the SDK and Connectors team, and I'm involved in the transactions development and design. I'm hoping to show today how we achieved the ACID guarantees that we have, along with the distributed performance at scale that we have. Let's start off with some background on transactions. SQL transactions were created decades ago for what was largely a non-distributed world. It was very common to be running single node mainframes with relational databases. And in that context, transactions are relatively easy. Isolation and atomicity gets a lot easier when you're working with a single node, when you're working with a database where you can easily lock pages or rows or the full database even. As soon as you start scaling a database up to multiple nodes, these things get a lot more challenging. And of course, that is the system that Couchbase is. We are a distributed system. So the challenge for Couchbase, for us engineers, was how do we provide the robust multi-document ACID guarantees that you're looking for, while keeping the distributed, scalable, share-nothing performance that we're known for. And hopefully this presentation will show you that we did and how we did. Before we start, let's briefly define our terms, because ACID is broadly understood, but it's not strictly defined. So what do we mean by it? As you probably know already, ACID stands for atomicity, consistency, isolation, durability. Let's start at the last one first, as it's easiest. Durability means that what's written stays written. It builds on the new durability feature in Couchbase Server 6.5, which basically means that when the application or the transactions layer performs a key value write, it goes to the active node. The active node takes care of making sure that it's replicated to all the replicas for that document before returning control to the application. That, along with a couple of other things under the hood, means that once a document has been written and acknowledged, it's safe, it's durable. This feature, by the way, can actually be used outside of transactions too. It's accessible through the regular key value API. I've got an example from Java here. You can just specify the durability level here. And there's various levels of durability. The default for transactions is this durability level majority, which means that the write waits until it's available in memory on the majority of replicas. There are additional levels of durability as well. You can also wait for it to be written to disk on either the active node or the active node plus a majority of replicas. So you have those additional durability safety options if you need them, but majority is a sensible default for the majority of transactions, we believe. So that is how we provide durability. Consistency, a very overloaded term. The consistency in the CAP theorem is not the same as the consistency in ACID. In the ACID context, consistency means that all database rules are followed before, during, after any transaction. In a relational database, that would include things like foreign key constraints that don't really apply to our non-relational database. So the rules that we do have, including that document keys must be globally unique across a bucket, all the rules that we have are followed during transactions. So we've seen how we do durability and consistency. Atomicity. The reason I'm doing this out of order is that I'm trying to explain the more complex ones last. Atomicity is all or nothing. It's the idea that all your documents either reach the committed state or they all roll back. So 99.9% of the time, this is going to be achieved inside your application by the transactions layer before returning control to the application. There are a few cases where we can't achieve it in that time frame. You give the transaction an expiry time, a maximum time it's allowed to run for. And there are times when if there's a node failure, we might not be able to fully commit or fully roll back the transaction inside that period. There's also cases where the application crashes in the middle of the transaction. So there are a few cases where there needs to be some cleanup. Cleanup is handled, and that's really the case in any database. We've tried to make our cleanup process as automatic and easy as possible. As soon as your application is running transactions, it's also kicked off a background cleanup thread that's taking part in a global distributed cleanup that's entirely automatic. So you have the ability to disable it on a per application basis if you need to, but we strongly recommend you just leave that running. And that will take care of the 0.01% times when it can't be finished off inside the application. So that's Atomicity. One thing I want to be really clear on in this presentation is that Atomicity, the A in ACID, does not mean that all the documents get committed together in a single atomic step. So we do provide an atomic commit, and I'll come to it in the next slide, but we don't provide it at the right time. It's simply too expensive to do in a distributed system. A transaction might be writing to documents across 5 different nodes. It's too expensive to try and do that in an atomic way. So we don't. Let me show you what we do instead. We provide an atomic commit, but we provide it at the read point. It becomes part of our isolation rather than our atomicity, if we consider atomicity being the write point and isolation being the read point. So coming back to that idea of the atomic commit at the write point quickly. So the original SQL standard doesn't really mention atomic commits at all. If you kind of read between the lines, it just sort of assumes it's working with a database where you can lock the database or pages of the database or rows and atomically update multiple documents at the same time. So as I mentioned, that's really just too slow to do in a distributed system. So what we provide is this read atomicity. And what happens is that the commit is eventually consistent by default. So the transaction reaches a commit point, which is atomic. I'll show how that works later on. And then each of the documents in the transaction is committed in an eventually consistent fashion. But readers that are transactionally aware, including the transactions library itself, have compensatory logic to handle this. They are able to detect that the document is in a mid-commit phase, and they compensate for that. They will actually return the post-commit version of the document rather than what's in the document at the moment. So what this allows is that we can still provide an atomic commit. We can still provide the ACID guarantees, but we can do it in a way that doesn't require these sort of heavy global locks, which really helps us achieve the high performance that we have. And the big advantage of this approach of using read atomicity, doing it at the read point rather than at the write point, is that you pay only for what you need. Rather than having to pay for write atomicity on every single transaction, you pay for read atomicity only when you actually need it. So if you do need read atomicity, you use transactions for reads. And if your transaction is only doing reads, it has almost zero overhead over a simple key value read. You also have the option to do index consistency, such as for Nickel, for query. That has an existing feature called at+, where you can ask for the query to be run only after the index is consistent with a particular write or a particular set of writes. And our API gives that ability. At the end of the transaction, you can ask for an index. You can do a query after a transaction and ask for that query to be consistent with the transaction that's just been run. So that allows you to handle the read your own rights case, which is quite common. But if you don't need that read atomicity, which is very common, you can just use the eventual consistency, and that's the default across Couchbase. You can also mix and match the approaches. Use eventual consistency most of the time, pay for read atomicity when you need it. So let's talk about isolation. We've already, as mentioned, that read atomicity is very much part of isolation. On a broader topic, isolation is really, it can get complex, but what it boils down to is what happens when two transactions interact. And they can be reads or writes of the same document. So what do we provide? We state read committed. It's really a little bit more complex than that. It's really quite a bit above read committed. So starting at the bottom of the stack, you have read uncommitted. This means that if two transactions are trying to write the same document, that will be detected and handled. The way we handle that is that our API allows us to retry transactions. I'll come to that later on. So what we do is if two transactions are trying to write to the same document, the blocked transaction will wait a little bit for the other transaction to complete. If it doesn't, after a certain period, it will roll itself back and it will retry. And the reason for that is to prevent live locks and deadlocks. It sort of releases any documents it has locked so that other transactions can have a chance to complete. So we safely handle write-write conflicts, as you'd expect from transactions. Read committed means that you can only see committed data. Most transaction implementations, including ours, work by first staging all the changes for a transaction somewhere. And then they reach, if all that successfully completes, you get to a commit point, and then you commit or unstage all of those changes. So read committed means that you can never see the staged changes. You know, the transaction has to commit before you see any part of that transaction. And we provide that across the entire Couchbase data platform. You won't see that unstaged, dirty data. But we go beyond that. We do go beyond read committed as well. We actually provide monotonic atomic view isolation. This is not a well-known term. I should say, by the way, this image is taken from Jepsen. It's a very good hierarchy of isolation models. This monotonic atomic view is taken from an influential paper about 6 years ago, written by Peter Bayliss and others, called Highly Available Transactions. What it essentially defines is the atomic commit at the read point. So this is what we were talking about earlier. It's read atomicity. It's providing an atomic commit, but not at the right point. So it's a very interesting paper. It's well worth digging into. It's one of the first papers that really started defining what transactions mean in a distributed system, and it was very influential on our design. So we are monotonic atomic view. We also provide, we prevent lost updates, which is what cursor stability prevents. Isolation levels, by the way, are often defined in terms of the issues or phenomena that they prevent, and cursor stability is designed to prevent lost updates. But cursor stability comes with a lot of baggage. It's very heavily associated with SQL concepts like SQL cursors. So we don't claim cursor stability isolation level, even though we do prevent lost updates. We just think it will cause more confusion than it solves. Finally, repeatable reads means that if you read the same document inside a transaction, you're guaranteed to get the same version of the document back, even if it's changed. It's usually built atop MVCC, multiple version concurrency control, meaning you have multiple versions of each document, which allows you to sort of have a snapshot of the world at the time the transaction started and act on that snapshot. So we don't offer that form of repeatable read with MVCC. We don't offer MVCC. We feel it's slow. But what we do offer is a way of easily performing repeatable reads anyway. There's a mechanism for, you can detect if the document has changed from when you last read it, and then you can easily ask for the transaction to be rolled back and retried. Our API allows that. So I won't go into detail on that, but that's an interesting concept, and it's something you can do with us. So our isolation level, hopefully I've shown, we claim read committed, we're really well above read committed. I actually call it read committed plus plus. It's a really good blend of performance and usable isolation. Above all, what we really wanted to do was just present a usable system without surprises. So what you'd expect from transactions is you don't see dirty data. We have that. You don't have write-write conflicts, or write-write conflicts are prevented against. We don't have that. Sorry, we do provide that. And you kind of assume there's going to be an atomic commit step as well. Many people assume that's part of read committed. It's really part of monotonic atomic view. But regardless, we provide that as well. And you also don't really want lost updates. So we provide lost updates, even though it's not really part of our stated isolation level. So it's a very usable system. Like the aim was to prevent surprises, gotchas, and we hope that's what we've achieved here. What we don't provide is snapshot isolation and serializable. These are almost always based upon MVCC, multiple version concurrency control. They also tend to require being able to globally order your transactions, which can be very challenging to do. So both of those techniques are slow, we feel. We think that the approach we've chosen is going to be very much more performant. And we also feel that many production databases do not work in serializable or snapshot isolation out of the box. Read committed is a common default for popular production databases. And there's a good reason for that. It's much faster. So yeah, our isolation level, read committed, but really much higher. So hopefully I've shown that we are genuinely ACID. We have atomicity, consistency, isolation, and durability. And hopefully I've shown how our atomicity and isolation in particular work. And I think possibly the concept of read atomicity might be new to some people, but we feel it's what makes sense for a distributed transaction. So we think this is how we achieve the performance, and this is how we achieve the atomic commit without slowing you down. So when would you actually reach for transactions? And you might find it weird that somebody who's involved in the development of transactions is telling you to not always reach for them, but that's what I'm going to do. Because our transactions do provide scalable performance. But as with any database, there's some overhead to them. It's not huge. You shouldn't be afraid of using transactions. The cost is not incredibly prohibitive, but the single document data model, which we've recommended for years, should still be your go-to 90% of the time. JSON is an incredibly flexible format. It allows things, instead of having separate customer and order documents as you would need to in a relational database, a non-relational document database allows you to have a customer that contains an array of orders. So now if you need to update customer and order together, you don't need transactions anymore. You just update the customer document. And that's really, if you're aiming for a really performance scalable system, that's really the approach that you want to be taking 90% of the time. But transactions now exist and they do bridge that 10% gap. So it's a tool in the toolbox. Don't be afraid to use them, but don't make it the first choice. Don't design around them, I would recommend. One thing that we wanted to make a real focus, and staying on the performance theme, is that transactions would have zero impact on the rest of the Couchbase data platform. Transactions exist as an isolated independent layer atop our very strong key value performance. So whether you're using transactions, whether you're not using transactions, regular key value reads and writes continue to offer exactly the same great performance that you're used to today. And that goes across the entire Couchbase data platform. Nickel, FTS, analytics views, eventing, I'm sure I'm forgetting one, but nothing is slowed down or affected by using transactions. You get eventually consistent commits across Couchbase by default. And then you pay for the read atomicity, you pay for the atomic commit only when you need to. So that's how we achieve that zero impact. Let's move on to talk about the API. I've mentioned a few times now that it allows transactions to be retried. So there were a number of goals we had with the API. An overwhelming one was to keep it simple, easy to use. So for starters, it's very similar to the existing SDKs that you're already familiar with. Instead of a get result, you get a transaction get result. Instead of collection.get, you do context.get. You still have JSON object, which is I'm looking at the Java API here, so some of these will be familiar to Java users, some won't be familiar to Java users, some won't be familiar if you're not used to the Java SDK, I should say. But the idea is that it's familiar. You can get started and jump in with this straight away. What we very much wanted to avoid was having to write your transaction in a very convoluted way, having to use some text-based DSL or something like that, trying to express conditional logic in that sort of complex manner. So reads are synchronous. When you do the context.get call here, that is performing a read at that point. And then that means that you can now just do straightforward conditional logic on the document that you just fetched. You can see has the user got enough balance to be able to do this transfer. This example, by the way, is a very simplified example. It's transferring money from one user to another. So first we get the two users we're looking at. We get the content, the JSON content of the users. We have a look at their current balance. If the first user has enough money to make the transfer, then we update the JSON in memory. And now we do a context.replace, and that's going to stage our changes at that point. So at this point, the changes are not yet visible to any other part of the Couchbase data platform. They are staged. If the user did not have enough balance, then we throw an error to indicate that. And if we get to the end of the Lambda, then the commit happens and the documents are committed. We'll come back to the mechanics of that a little later. So you provide your transaction here inside this inside a Lambda, an anonymous function, a callback. The Lambda gets provided with a context object. Everything that you do want to do inside the transaction, you do through that context object. So I can do reads here. I can do replaces. It's also possible to do inserts, removes. The real advantage of providing your logic inside a Lambda like this is it lets us retry and it lets us handle errors for you. For example, say you get to the context.replace point, that goes to stage that change, and that finds there's actually already another transaction writing to that same document, a write-write conflict. So we have the capability now to handle that without any intervention from you. We can just take care of all this complex error handling for you. The exact logic done here is that we would wait a bit for the blocking transaction to finish. And if it doesn't, we would roll back everything we've done so far. So we're not locking these documents indefinitely. We would have a little bit of exponential backoff, and then we would retry the transaction from the top. And that all happens completely under the hood. So what you do is when you provide how long you're willing to give the transaction. By default, it's 15 seconds. And then inside that 15 seconds, we will try and get the transaction done. So really aiming for a very easy to use API that just takes care of this complexity and these details for you. I'm showing here the first of the two APIs. This allows doing it's a sort of synchronous blocking API. There's also a second API that allows parallelism of KV operations using the if you're used to the Java SDK, you might know there's a reactive API that's part of it based on Project Reactor. We have something very similar for transactions. And the other languages that support transactions can offer this as well. So let's have a look and see what happens under the hood. We've got a very simple transaction here. We're getting two documents, user A, user B, and then we're replacing the contents of those two users. I haven't shown actually creating the new content here, just to keep it brief. So our transaction is writing to document A, which is user A, and document B, which is user B. Document A is on node A, document B is on another node C over here. So the first thing that happens inside the transaction, well, first the reads happen. And reads are basically, they have almost zero overhead over an underlying KV read in the majority of cases. So the reads happen. Now we get to the first mutation. As soon as there's a mutation in the transaction, we need to write a little entry for this transaction. We need a single point of truth over whether the overall transaction is committed, expired, these types of details. So where we create that entry is there are these active transaction records, ATRs. There's a minimum of 1,024 of these documents, and they're created on each bucket that is doing transactions. They're automatically created and maintained by the transaction library. So please just ignore them, let them do their thing. The ATRs, what they are is many database implementations will implement transactions using some sort of transaction log, kind of a record of all transactions that have ever occurred. Our ATRs are kind of like that, but they only store currently active transactions, ones that haven't sort of expired or been cleaned up yet. And instead of having a single transaction log, which is kind of a major point of conflict and contention, we distribute this active transaction record across these 1,024 individual documents. So this allows us to really, this is a cornerstone of how we achieve the distributed performance at scale that I'll come back to that on the next slide. So the first mutation goes ahead and it picks an ATR. So each ATR document can contain multiple transaction records. Just because there's 1,024 ATRs doesn't mean you can only run 1,024 transactions at a time. The ATR chosen is always on the same node as the first mutated document. In fact, it's on the same V bucket if you're familiar with Couchbase architecture. So it will follow that document around as well in the event of failover. And the reason we do that is that if your transaction only needs to touch documents A and documents B on these two nodes, those are the only two nodes that you really want to be involved in the transaction. You don't want to unnecessarily pull in node B because that's going to somewhat affect your availability, which becomes a bigger issue when you start getting to 20 node, 30 node clusters. So this is part of how we provide what sort of highly available transactions. This transaction would not be affected at all by node B going down. Then after we've written to the ATR entry, we stage the new contents of the transaction alongside each document. This uses a feature called extended attributes, which is some metadata associated with each document, and it allows us to do this very performantly because this kind of look-aside data can just be kept right there alongside the document, which makes reads and writes very efficient. If anything goes wrong during this stage, then as mentioned, we will just roll back everything that's been done so far. And then we will either fast fail the transaction or we will retry the transaction depending on the error. And if we believe that the error will be resolved on a retry, such as a write-write conflict, would retry the transaction. If all of this was successful and no exception was thrown and we reach the end of the Lambda, we commit the transaction. So we go ahead and go back to that ATR entry we created earlier, we flip it to committed. And now from the point of view of transactional aware actors, such as the transactions library, the whole transaction is now atomically committed. I mentioned you have this read atomicity. This is the signal for read atomicity to take place. So the actual commit now happens. Each of these documents gets committed or unstaged in an eventually consistent manner, but read atomicity is performing compensatory logic for it in the readers. So you do now have that kind of atomic commit step. And finally, when it's all done, the ATR entry is completed and removed. This is a huge part of how we achieve the distributed performance at scale. We've seen one transaction taking place there, but let's scale it up a tiny bit and now look at a 4-node cluster with a couple of applications running against it. So application A is performing this transaction and it's writing to documents on A and B, and it's going to write to an ATR document on node A because the first mutated document is on node A as well. Application B is doing a second transaction and it's writing to a completely unrelated set of nodes. It's writing to documents on C and D. Now, the great thing about the architecture that we've written is that there is no interaction between transaction 1 and transaction 2 here at all. They're not touching the same document, so they don't need to interact, and they don't. Because notice what's not on this diagram. There's no point of coordination where both transactions are also having to write to a global transactions manager or a lock scheduler or a timestamp distributor or any of these single points of failure or contention. So this means this can just keep scaling very, very well. So this is really a huge part of what we're aiming for with the architecture. We have the transactional clients exist here and the transactions layer, and they just drive the whole thing from the application side. There's no server-side coordination taking place. So this can really just use your application server resources and just scale up as well as you need it to. I guess we've reached the summary point. Hopefully I've shown you that we offer true ACID transactions in a distributed system. I think possibly the only part of the ACID definitions that might be a little bit unusual is providing the atomic commit as read atomicity rather than write atomicity. Hopefully I've shown you why we feel that's necessary and why we feel that achieves the performance that you're looking for and why we did it that way. I hope I've shown you that the whole system is very easy to use. You've got a simple API that takes care of error handling for you. There's a cleanup process, as almost every transaction implementation requires, and it's fully automatic. You just don't need to worry about it. It's just kicked off in the background when you start doing transactions. And overall, there's just no surprises. There's no gotchas. We've aimed with the isolation model to provide something very useful. We've gone beyond our stated isolation level of recommitted to also prevent lost updates, because lost updates can be a real surprise, one that you don't want to deal with. I hope that I've shown that we provide distributed scalable performance. There are no single points of failure. There are no points of contention in the system. The whole architecture can scale very well. And I hope that I've shown that you only need to pay for what you use. There's no impact from running transactions on the existing strong Couchbase performance that you're used to. You get an eventually consistent commit by default, and then you just pay for the atomic commit. You pay for the read atomicity only where you actually need it. So wrapping up, you can get started right now with transactions for Java. The transactions layer is available as a separate library. You don't need to configure any new resources on the server. The library has been available since January of this year. It was released alongside Couchbase Server 6.5. The dependency for the current version of the library is Couchbase Server 6.6. We have so many documents, so many example projects. You can just get up and running straight away. And we have documentation for the server-side transactions as well. Sorry, I should say server documentation for the transactions. We also have transactions implementations for C++, .NET, and Go under very active development as we speak as well. And there's plenty more to come for transactions in Couchbase 7.0 and beyond. I wish I could cover some of the fantastic features that we're working on for that release, but please just stay tuned. I think they're going to be very exciting. And yes, that about wraps me up for today. I've been Graham Popel. It's been a pleasure to give this presentation. Please hit me up with any questions that you have in the text chat. And thank you very much.